So hi everyone, my name is Kyriel. I'm currently a Year 3 undergraduate at NUS. And today I'll be presenting some joint work with Professor Martin Henz on a Notional machine that we have designed for Scheme. So for some background, the two of us work on a platform called Source Academy. And this is an educational platform designed to support CS111S, which is NUS's CS1 course based on SICP JavaScript edition. So in order to aid the teaching of CS111S, we have several tools in Source Academy. Namely, we have an interactive version of the SICP book. So students can go onto the website and read the book on our platform. And if they want to see any examples and actually execute them, they can execute them in the browser itself. We also have this tool called a stepper, which we have previously presented in Splashy 2021. Essentially, what this is a program evaluator based on the SICP substitution model. General sense of the CSM machine through some simple examples. So on that note, let's start with our first example. So in this first example, we are just going to evaluate the value of the result of multiplying 2 by 3. So whenever the CSM machine starts its execution, it will always begin with an empty stash, the base environment here represented by E0, and a control consisting of just one item on the control, in this case, the entire program. So the CSC machine operates by evaluating the topmost component of the control, either by decomposing whatever expression is there into simpler sub-expressions, or by executing what we call instructions. So in this case, we have a procedure call here, and it is decomposed into sub-expressions, namely the operator, the multiplication, the operands 2 and 3, as well as what we call a call instruction. So evaluating this, the next step is to evaluate what the variable asterisk. So what happens now is we will look into the base environment to see what value this variable is bound to. In the base environment, we assume that all primitive operators, such as multiplication, division, and whatnot, are already all bound to their specific variables. And so we just look up the variable and we see the times operator and we put it on the stash. Okay? And next up, we evaluate two primitive values, namely 2 and 3. So what happens is they are directly evaluated and placed on the stash. So we do this twice for 2 and 3. And now this comes the interesting part, which is the actual application of the procedure. So what call2 does is it takes the topmost 2 items from the stash and it applies them to the very next item in the stash, which is the times the multiplication procedure. So what happens now is we just evaluate 2 times 3, and you'll get 6. And the resulting value is placed on the stash. Now, what do we do? So again, we look at the control, and hey, it's empty. And since it's empty, there's no more things to evaluate, and hence, the program terminates here. Yeah. So I hope that all of us here, we get a sense that if we continue to explain the CSC machine using this notation of triples and transitions, it's going to become a nightmare, especially because in this case, we already, just for a simple multiplication, we've already had to describe 6 different states. Now imagine what happens if we try to describe a more complex program, like a meta-circular evaluator. It's going to be a nightmare. There are going to be hundreds of states. And so, so we agree as well, like using this representation is not how we intend to teach a CSC machine. And for that, we actually have a tool in Source Academy we call the CSC Environment Visualizer. Let me show you what it looks like. So we argue that this visualization is much easier to teach to students, and this is how we intend to teach the CSC machine. So again, going to Source Academy, we are on what we call the playground. So on the left side, there is an editor, so I can edit my code. I can say, okay, I can add another command. And if I want to evaluate my program, I can just click run here. And hey, yeah, 2 times 3 equals 6, right? Oh, yes. Okay. But now I want to see how the CSC machine actually executes. So you see this flashing tab. This brings us to the CSC machine. So right now what we see is the entire environment tree of the program. But to actually see the CSC machine, we have here the control and stash button. So if we click it and we press run again, let me explain what it looks like. So the control is here. It is visualized as a vertical stack, whereas the stash is a horizontal stack. Right now, you don't see the stash because there's nothing in the stash, right? So if we actually evaluate the program, the very first state contains just the entire program on the control. And another thing we see is an additional procedure call for the make number procedure. We will get into this later, but for now, just understand that this produces a scheme number, okay? So in line with what we've previously discussed, we can see the transition of state to state by using these buttons here. So we can go back to previous states, we can go forward, we can go to the start of the program, we can go to the end, but we can also use the slider on top to go to whatever state we want. Yep. Okay. So the takeaways from this example is that the CSC machine execution is fully dependent on the control. So it proceeds and transitions to the next step based on the topmost item of the control, and it terminates execution when the control is empty. And the semantics of how the CSC machine proceeds are fully based on expression decomposition and instructions. So going further into what instructions actually are, so instructions are control objects that are generated during program execution, and they are byproducts of expression decomposition. Now, each instruction in the CSC machine provides a simple operation which is relevant to explain how the program evaluates. And for Scheme, we have a minimal set of 5 instructions that fully describe all of the operations required for SICP Scheme. And for example, the call instruction, as we've already seen, handles application of functions or procedures or mathematical functions. The assignment instruction handles assignment, yes. And then the branch instruction handles conditional logic. So for a more complex program, we have factorials. We have a program of factorials. Factorials are very popular today. Yep. So before we execute, we see what's actually happening in our program here. We define an n, n equals 6. We define a very basic factorial function, and then finally we calculate the value of factorial 3 and we add it to n. Okay. So once again, we run the program, and we see that the resulting program is, the resulting value is 12. It's just factorial 3, 6 plus 6 equals 12. But more importantly, looking at the CSC machine, again, we start off with one item on the control, which is the entire program. The first thing to do is to split the entire program into its constituent expressions. So there are 3 in this case, 2 definitions and 1 procedure call. So 1 top-level procedure call. So yes, the first thing we do is we define n to be 6. So what happens is we evaluate the value to be defined first. So we make the number 6 here. And then we assign it to n. And now we see that our current program, our current environment, which is highlighted, has now been updated to have the value 6 bound to n. Okay? So now the value 6 is no longer required on the stash, so we pop it, we remove it, and we do the same for a factorial. We evaluate the lambda function first, the lambda expression, yep, and we assign it to factorial. Okay? Now we actually do the fun stuff, which is the actual application of the value. So first off, we evaluate the plus, yes, but now, and we look up the value of factorial, and yes, it corresponds directly to the closure already defined here, right? And then we make one number, okay, sure. And now we call the actual closure here. So what happens for the call instruction when calling a closure is that the body of the closure will be placed on the stash, on the control. So now we evaluate what this means. The body of the factorial is just an if expression, conditional expression. So in evaluating a conditional expression, we first need to evaluate the value of the predicate. So how the conditional expression is decomposed is that the value of the predicate is evaluated first. And in this case, we evaluate whether n is less than 2. So we compare n and it's 3. 3 is definitely not less than 2, so it's false. Okay, so now that we've evaluated the predicate, we actually need to decide which branch to take. So the branch instruction handles conditionals, as I mentioned earlier. And so now we want to understand whether we want to take the consequent or the alternate branch. But seeing this branch instruction alone, I want to see exactly where in the program it corresponds to. So if I hover over the branch will highlight the part of the area in the program it corresponds to. And now I can easily see that, oh, okay, my consequent is 1, my alternate is a recursive call to factorial. So because the predicate is, yes, sorry?
Without doing that hovering over, can you see what the branches you're choosing between are? Because I don't see them over on the right side.
Sorry?
Without doing that hovering over, is there a way of seeing which 2 branches are being chosen between? Because I don't see it on the right side. I don't see it in the CSC.
In the branch.
It's in the branch?
Currently, there is no way. We are looking for better representations for the branch instruction, but this is what we have for now. Yeah.
Bit of a related question, but I see these very nice box and pointer diagrams which we use to represent environment models.
Yeah.
And I wonder if I can get the whole environment model for example, factorial, because sometimes when I'm teaching, I really don't want to draw it myself on paper and by hand. And I thought this would be excellent tool for box and pointer diagrams. Is it possible to get a box and pointer diagram from your solution here?
Box and pointer diagram.
Yeah, it's essentially showing how the environment model works in Scheme.
Yeah, so this representation is fully based on SICP's environment model. So if I were to, I'll just skip to the end of this evaluation. By the end of this expression, you'll see the entire environment diagram displayed on the screen. Yeah.
Is it really that hard? I thought it would be more complex, but that for factorial one. Is it factorial 3 or?
Yeah, this is factorial 3. Yeah.
Okay, that makes sense. Thank you.
Okay, so let me go back. Sorry. Yeah, so this entire execution handles the evaluation of factorial. And by the end of it, we see that, okay, if for the recursive call to factorial, over here, right? Currently, the current environment is this environment here, where we have a binding of n to 3. And so if I evaluate the value, the value of factorial, what happens is I want to look up in the environment where factorial is defined. So the current environment is here, but I want to look up factorial. So, we have a binding in the enclosing environment. So we can just use this binding, and from here we can handle recursive calls. Yep. So we continue evaluating the program. We continue doing more recursive calls to factorial until we have the value 6, right? Hold on. Right, here. So now at this point, we have the value 6 from the factorial on the slash. But now I want to evaluate the value of factorial 3 plus n. And we know that this n does not correspond to the n bindings in the factorial environments. So we have this instruction here, the environment instruction, which returns the environment back to the enclosing environment, right? So it returns to the original environment here, where we have the proper value for n, which is 6. So we load that value up, and we add the two values together, and we get 12. Yep. Okay. So, yes? Sure. Yeah.
So if you were to make the factorial tail recursive, will I still get the box diagrams? Or?
Sorry, what do you mean, tail recursive?
So instead of like using, as in at the end of the recursion, you want to return the results. So you keep accumulating, and at the end of the recursion, you just return the results instead of unfolding the whole stack. Will I still be able to visualize the box and pointer diagram?
Yes, even for this box and pointer diagram environment model also works for tail recursive functions. Yep. Sorry. I want to correct myself. Tail recursion optimization is not something we have in the environmental model yet. So we just want to teach the basics, which include the creation environment frames and whatnot. Yeah. So originally, this was the whole scope of the CSC machine, which was to handle conditionals, recursion, definitions, and the like. And this alone allowed the CSC machine to explain everything required for a SICP scheme. But it was at this point that we realized that we could go further beyond and go beyond SICP scheme and tackle the idea of continuations as well, because all of the building blocks were in front of us. All we needed was a way to represent continuations, and so how do we represent continuation specifically? We just go through, we just get the idea that a continuation is nothing but a program state. Why? A program state includes the control, stash, and environment. The control tells us what we need to do. The stash tells us what we still need, the values we still need in order to do what we need to do, and the environment tells us in what context we do it. Given a single program state, we can give it to the CSC machine and it will compute the rest of the program for us. So a state is the rest of the computation, which is what we understand for computations, for continuations as well. So we can use the same representation for continuations, for program states, to describe continuations as well. So how do we actually enable first-class continuations in the CSC machine? The first thing we need to do is to reify continuations, i.e., we allow these program states themselves to be values that can be stored in the stash or bound to variables, right? And in this case, we use a different constructor, the cont constructors, to increase the legibility, to improve readability, right? And now we actually need to have a way to activate the continuation. And in Scheme, how we activate continuations is to apply them. So this requires an extension of the call instruction in order to handle continuations as well. So what happens when I actually apply a continuation? The very next step after this, after I apply the continuation with the call instruction, is that the values of the control, stash, environment in the continuation will override the current program, their corresponding program values. And so the very next state after this would be this. Everything has been replaced, and we have effectively returned the program to the point at which the continuation was captured. But on that note, we also need a mechanism to capture continuations. And in Scheme, this is handled mostly by call CC. So call CC is the main mechanism to generate continuations, and it does double work. Namely, it generates a continuation, but it must also set up the call of the procedure given the call CC with the continuation. And so our rule in the CSC machine may seem a bit confusing, but I'll try to break it down step by step. So first, we evaluate the call to call CC here. And so at this state, I'm sure that it looks obvious that this is the continuation we want to capture, right? So if we break down the call CC procedure call, we just call this, and now we have this state. After this, after we call CC with F, the first thing to do is generate the continuation, right? So we generate this continuation. But now we also need to prepare the procedure call for F with the continuation. And so what happens now is we put F back on the stash, and we add call 1 back onto the control. And so effectively what this does is that we call F with the continuation as its single parameter, right? And so we have an example of continuations in play in Source Academy here. So what I'm doing here is I'm using a continuation that we are bound to the variable ret as an early return mechanism, right? So this will never execute. And if we actually try to run this, we can see that, yeah, it works. Late is never evaluated, and we get the value early instead. Now let's look at the actual CSC machine. So let's run this again. Again, we do the definition of F. Yes, we can skip past that. And then we do the actual call CC evaluation. So we evaluate call CC. Yes, and now when we call CC, what happens is we produce the continuation here, and now we call F with the continuation. So now the ret variable is bound to the continuation, and now we evaluate ret early. We call ret with early. So what happens is we load up the continuation, we load up the value of early, and now we call this immediately. And what happens is, as you can see, the continuation overrides the program state in the next step immediately. So we just get the value early, and there are no more things to evaluate. Yep. So moving on to how the CSC machine actually benefits learners. So actually, the CSC machine has already been in play for about a year now, It's been integrated into the course and is introduced after students learn the environment model. So actually, there are two different Notional machines already in SICP, and they are introduced in Chapter 5, where the interpreter and compiler in Chapter 5 could be seen as Notional machines. But we chose not to use these two Notional machines because they are based on registers, which we felt were too low level for introductory CS students. And we felt that the idea of registers could be better introduced in a more advanced course after our course. And going on to how the CSC machine is inspired from other SCC machine variants. So many variants have avoided the dump component of the SCCD machine in different ways. For example, the modern SCCD machine uses a global operand stack, while the closure machine combines the dump and control. So we take these ideas, we use the same thing, use a global operand stack, but we also use the environment instruction to add the environment restoration instructions on the control. And doing so, we avoid the dump component, and hence we simplify the semantics of the CSC machine to a level we argue is understandable for year 1 students. Yeah. So other machines also use the idea of de Broglie integers, which simplify the concept of environments, because now environments are nothing but a list of bindings to variables that I can just look up immediately. But this requires a pre-compilation of the program that we thought would be confusing to year 1 students. So we avoid the use of these integers, but in doing so, we have made the idea of environments much more complex. But we felt that this was not an issue because we could just piggyback on SICP's environment model to explain to students how environments work. Yep. So in implementing the CSC machine, actually we lied a bit because the CSC machine that we use is a common CSC machine between Scheme and JavaScript. So Scheme is actually, in Source Academy, Scheme is designed as a transpiled language. It transpiles down into JavaScript, and the CSC machine operates on the JavaScript code. And this may seem confusing, but it was chosen because in order to allow Scheme to use all of the tools that were already designed for JavaScript in Source Academy. But however, this transpilation leads to many different transpilation artifacts that we can see. For example, the make number procedure earlier is required because Scheme in our implementation uses numbers that are consistent with Scheme's number tower, but these do not exist in JavaScript, right? So this implementation approach leads to the hope that we can transpile different other languages down into Scheme. And we choose Scheme because Scheme has macros and continuations, which can use to represent many different control mechanisms that are more complex in other languages. So by using Scheme as a baseline, we could transpile languages down into Scheme and in doing so use the CSC model, the CSC machine, as a common framework to understand how other programs in other programming languages execute. So future work for this CSC machine. Currently, I mentioned macros, but they haven't been implemented yet. They are the goal of this semester. We also want to work on hiding transpilation effects from users so that it will be a more seamless experience. And we do not have a diagrammatic representation of continuations yet. We would like to work on that as well. So in summary, we have this Notional machine. It operates on expressions and instructions, piggyback and extends the SICP environment model. Hopefully, in the future, we can use this CSC machine to capture the mechanisms of other programming languages as well. Yeah, thank you.
So we don't have that much time for questions. Anyone have a question?
Thank you for your talk. Your CSC machine accommodates code CSC mechanism, but can your machine accommodate delimited combinations?
Sorry.
Can your CSC machine accommodate delimited combinations? Such as shift or reset or control prompt?
Currently, we do not have that.
Yes.
So we only work on unlimited combinations.
Yes. Any insights to implement such mechanism?
I was planning on using macros as well as continuation in order to provide the mechanisms for shift and reset, because I know that there has been previous work to represent both using concise and macro transitions.
I think.
But we also have the possibility of implementing other instructions into the SICP Scheme in order to make these mechanisms more seamless, instead of representing them using the minimal subset of instructions required.
Thank you.
So I have a very naive question. So this machine looks a lot like the CEK machine. What are the differences, I guess? Like when you look at the visualization, to me it looks exactly like a visualization of a CEK machine. So why this formulation versus the CEK machine, I guess?
By the CEK machine, you mean?
Like one of the Felicen machines that just includes continuations of an explicit component, for example. I think it's possible it's isomorphic. That might be, that's a question that I have, I guess.
So actually, we chose not to use the CEK machine because we felt that continuations as a whole were a bit confusing for year 1 students. I know that this may sound a bit confusing considering that half of my presentation has been on continuations.
Right.
But the point was that we wanted the basics of the CEK machine to be simple. So we wanted to avoid the idea of continuations. But because we could represent continuations using these simple mechanics, we opted to go this way instead.
Makes sense. Thank
Yeah.
you. Appreciate it. All right, let's thank the speaker again.